say what goes up must come down, but in the Red River Valley, there's a soil phenomenon that's just the opposite. I'm Tom Fuchs, the Senior Construction Manager for the Metro Flood Diversion Authority, with the second part of our series on Red River Valley soil. In part 1, we examined our area's history and looked at the layers of soil. Most of those layers are weak and highly compressible. Given that, what does it take to engineer permanent flood protection in the Red River Valley? The FM Area Diversion project's main components include 3 large, gated control structures, a 30-mile channel, a 22-mile earthen embankment, 2 aqueducts, and numerous inlets and crossings. Miles of driven steel pilings support the aqueducts and gated control structures, ensuring they're supported on the deep glacial till soil. Roughly 40 miles of steel piling lie under the 3 control structures, extending to depths between 80 and 110 feet below the surrounding ground surface. Another 9 miles of steel piling will support the Maple River Aqueduct, and nearly as much will be used for the Cheyenne River Aqueduct, where earthen embankments meet structures that are founded on piles, such as bridge approaches. Differential settlement can occur, meaning the embankments will settle faster and more drastically than the adjacent structure. To combat this problem, engineers use wick drains and surcharge embankments. Wick drains, which consist of a flat strip of corrugated plastic in a permeable geotextile fabric, are placed vertically into the soil to allow water in the pore spaces of the clays to have a shorter flow path as the surface load is applied. Increasing the load through additional fill placement, known as preloading or surcharging, results in the water being squeezed out faster than it would be if it naturally was pushed out into the surrounding area, since clays have very low permeability. Theoretically, by the time a bridge structure is completed, the soils supporting the approach embankments on each end have already settled. Even areas without above-ground structures, however, still require a unique engineering approach here. Most of us assume that soil settles, and it does, of course, but in the Red River Valley, it can also rise. Our weak underlying clays have been in a natural state of compression from the weak overlying soils above them for thousands of years. So, in areas where excavation extends deeper into native clays, such as the stormwater diversion channel, the soil relaxes, resulting in vertical expansion. Think of it as a brick on top of a sponge which compresses it, and removing the brick allows the sponge to spring back to its normal shape, with the difference being that the clays don't spring back as quickly as a sponge would. As ASN constructors builds earthen embankments along the channel, the soils beneath the embankments begin to settle while the channel bottom begins to rise due to the unloading. In other words, what goes down must come up. Alternatively, elements are designed to withstand the forces of vertical movement caused by the uplift or rebound. When it comes to the stormwater diversion channel, which is designed to move floodwaters around the Fargo-Moorhead metro area, the solution lies in over-excavation. Crews are excavating up to 2 feet deeper than the necessary channel depth, with the expectation that the clays will rebound to the desired depth. If this seems counterintuitive, it probably is in most locations. However, it is critical that the channel's required volume for holding water from major flood events is maintained after construction. Besides considering settlement and rebound when designing structures, engineers also take into account that the soils in our region are prone to slope instabilities. Different types of slope failures can arise in the region, including surface sloughing, erosional slumping, and deeper-seated rotational failures. Sloughing, which is sometimes referred to as surface creep, typically occurs near the surface of exposed slopes, as they will be with the diversion channel. These failures are often shallow and may be caused by interaction with surface water during heavy rain events or after the surface soil goes through freeze-thaw cycles, which result in loss of cohesion. Erosional slumping is common on riverbanks, such as the Cheyenne River, where the silty clays are washed away near the river bottom and a portion of the bank soil simply falls due to gravity and lack of support for the soil's weight. To mitigate this, engineers use a supporting wall along the bank or add riprap to protect the bank from erosion. Rotational failures often occur deeper in the soil column than sloughing or slumping. Failures may be due to simple forces caused by the soil's weight, but also can be influenced by human activities, such as constructing buildings too close to the critical slope failure plane or allowing water to seep into the slope, which adds weight from activities like lawn irrigation. To help reduce the potential for slope failures throughout the life of the project, engineers performed slope stability analyses and designed the diversion channel sides to provide a safe slope during extreme hydrologic conditions. Additionally, ASN Constructors is constructing various drainage systems along the channel for water management and installing riprap to reduce the water's potential for erosion within critical areas near structures. Although settlement and rebound must be estimated based on representative soil sampling and testing regimes and are not exact sciences, years of engineering experience has taught us how to manage these phenomena and the combinations of challenges they present. Understanding the geotechnical challenges of the Red River Valley helps us better understand not only flooding and things we witness along the riverbank, but also the amount of ingenuity that has gone into this engineering marvel. If you would like to learn more about the FM Area Diversion Project, visit our website or subscribe to our monthly e-newsletter, The Diversion Current.